is just you know, you know. So again, identical training easily performs, and even this energy violating escapes, even early times, it does not see. This is just a summary of, at the end, I just put down some of the papers. All this was based. And, if you have to sell an idea, you have to bunch of exercises. And indeed, we did coupled bistable oscillators, d-dimensional Horton oscillators. But the bottleneck is the same. Each is almost the same. I have 3 minutes. Yeah, 3 to 4 accelerated minutes. So this last bit, I'm sorry, I'll go a little bit because like I should finish in a few minutes. So this is the last idea in this. Now, all of this was fine when someone asked us, "Oh, what kind of data we get from observation?" Even know that they are phenomenal variables. So if you didn't put a variable into your thing, how badly do you do? Because this is an issue. We recognize it's an issue. Then we thought, okay, just enhance our works. So give it any old variables. Why? We put in a layer which maps that uh, always pictures better, which maps it onto. So we have these two distinct units. We concatenate it and essentially give any old variables. But what if internal mapping it does? It should put a set of variables whose Hamiltonian loss is the least. That's okay. So we have made a slightly enhanced box so that we can deal with data like that. Right? So now we are unfettered by this task of finding canonical coordinates, which we know is quite hard because we give it to our classical mechanics students and they, are sweating it out, saying it's a very hard problem. Okay, but well, here we give 87. So what we tested it out are on things which I find interesting. One of this is the good old Vodka-Volterra, hydrogen atom of technology. The interesting is some versions of it actually has a Hamiltonian structure, something which even I had not thought of before. So we tried that. We tried, of course, the usual elastic pendulum, where there is a long link between radial and angular motion. And of course, so Luca wanted. It has a really non-trivial example actually of underlying Hamiltonians. Who would have thought sheep and rabbits have Hamiltonian structure? They are not related to any mechanical property. Okay, so you can't guess it. So here is, for instance, an Octa-Volterra system which looks like so. Neither variable nor their combinations are coordinate line or momentum line. It has constants of motion. Not all constants of motion are Hamiltonian. These are just fun things. But this one is. So if you do this particular transformation, you get a function which generates your flow. So bottom line here is, if I give you sheep and rabbits population, you would know from a general thing what your canonical variable is. So let us trade it. Sheep. Right. That's not. You say sheep and sheep. No. God, yeah. They are happily making more sheep and more rabbits. Yeah. True. Absolutely right. Need somebody to make it interesting. Yeah. Right. So this shows I'm not just anyway, here. So this is N1 and N2 populations. And this is a pseudo energy, as in the conserved quantity, constant quantity, which is for the true simply a constant. It's a neural network, it has. Like by now, I don't. So even the ancient learners in Hubei get no prizes for guessing why. Because you gave it coordinates which were not canonical. It was trying to fit a Hamiltonian function to a set of coordinates which were not giving that function. So it was trying to do something which was not correct. It was unhappy. So it had some something which was not as bad as this. if I put in my enhancers, given just these two populations, it managed to find that middle layer. So I will say this part. So elastic pendulum, again, nice example because the momentum mixes the two coordinates. So it is not easy again to guess unless you do all your homework. And so we just gave theta dot and L dot or L and theta and not the momentum. Let's see how well it did. So L theta, and we asked it to find out the canonical ones. Here is the bottom. This is the elastic pendulum. True. And then it does badly. H and N also badly. See how well this enhanced box does. Okay. So it has managed to find that layer which has guessed the canonical. Double pendulum, same result. Bad, pretty bad, and great. And this is data. Yeah, this is my second last slide. This is the data from a real thing. At the end of the day, somebody does an experiment and gives you a string of data. So this was the this is chip from which we took from a little mobile and fed that data in. So this is what we got. Okay. So that is the summary of this. It could forecast any general coordinate as well, uh, even though it didn't know. So I will end now. This is the outcome. So we have added that little extra ingredient of trying to make it respect the Hamiltonian structure. That's all we have done. Otherwise, identical. But gave huge dividends of you know predicting both in predictability and in just qualitative global structure. And these are the papers on which a lot of what I've said is based. And I'll take questions by keeping the news buzz thing. Some of it is accurate, some of it is overblown. And I'm open to questions, yeah. You know, let's start with questions. Yeah. First, we usually think of this group advanced as being big models, modifications, the stored patterns and stuff. Is it just by analogy that these are I mean, yeah. There is no, so there actually, so I would fill feeds and so trying to fill something by using these connections. So I had a, we used to say we used to do model neural networks, where we have models of neurons, we string them together. One neuron start make you have exactly as you said, or you have a tangent functions, that. So this is you're actually your focus is different. Your focus is this is my box. So this is my proposal for a box. But what you do box is different. You could do any on time. So put and fill the box so that it gives the best input out. I am simplifying it, but it's what you. Other one is a modeling approach. This is actually a engineering approach. So that's the pattern based. Yeah, this is there you get the pattern and you say, wow, this gives this pattern. You are filling the box to get the. And it says children require 8 by 1 knowledge of Hamiltonian. No, that's a very good question because I trying to understand. You can use Hamiltonian, then we have cheated like crazy. He wants to be. It doesn't know the Hamiltonian at all. Sometimes even we don't know the Hamiltonian. Like that clock video thing, I mean, we didn't know exactly what the truth was. It was something we set up in the lab. It's exactly something. So it doesn't know that at all. What it takes in is P's and Q's. There it took Q naught and Q input. Here it takes P's and Q's. All it does is that the loss function it assumes is that is generated by a Hamiltonian. So that's why it's an existence thing.
You haven't told me chaos.
It's just half. So the way I see it, that of course, lots of systems are not hammered. So sometimes I was thinking, maybe I use my black box as a test for a hammer. If it doesn't do well, then I know that there is no underlying structure. Or maybe those variables were not canonical. I could, because it's just a physics person. But yeah, strengths are wrong. So it's existence that there is, but not Hamiltonian function we know. No. That's not it. So you are, what are you approximating? Suppose you had a box. So either you have Q to approximate Q double dot. Then so you shall know that these instances maybe you can say your force function. In your head you can say. I'm not doing that. Here you're trying to say that the box has to approximate a function h such that if it had this, it would then. You don't know the function. You don't know the function. So you don't even know where the what it is. Even now I don't know the function. So what I've predicted. No. That of course you don't know. What you know is that this is what you wanted to do. You know what you want. What is the loss that you're minimizing? You expect that there is. So you have to approximate h. That is your one out. That's the
One short so my question was similar, like about the Hamilton. We are using Hamilton.
okay.
It's not done. But it's just that function that spans the Hamilton.
Schematic as the your box, your that's function that you're it's your outcome. So it's not you don't know it. If you knew it,
I think where you showed actually the picture, I don't know the equations,
uh,
but the way you showed the picture, it seems like you actually get the function. So, give me any you will give me the value of h. That no.
well, only thing as you know in the box, they don't actually you give okay. At the end you are giving the P's and Q's. I mean you